to take the time today to talk about the radius of convergence. Now this is something that we only get with these power series. Now if you've noticed with the power series, we end up getting x's in our terms. So we get an n in our term, and we'll be running as an index, but then we'll also have this x term that'll be kind of sitting there. Our x term will dictate where our series converges. We developed all these nice tests to figure out where our series converges, and now we're going to be able to look even farther into that with these power series. So today we're going to be talking about the radius of convergence and also the interval of convergence. So this is for the power series that we were discussing last time. We kind of already did a lot of it, but we're going to keep on going. So we have a couple of possibilities for convergence when we're dealing with a power series. So sometimes we will have a power series centered at A. So this is like an approximation of a function centered at A. So here we have the sum from n equals 0 to infinity of c sub n times x minus a to the nth power. Now this is again a repeat of what we had when we were dealing with the power series earlier. We already looked at this, but now we're going to throw in a little catch to it. So the series can either converge for x equals a, so it can converge for some value, or it can diverge for all x. So it can either converge at some specific point, or it can diverge for all x, so then the series diverges, or we could converge for some interval that the series converges for. So we could converge for some instance where the absolute value of x minus a is less than r. We call this r the radius of convergence. So if we converge for a little bit here, so if I have a function, something like this, and we have a series representation of the function, their series representation for the function goes up to infinity, but then it converges for this little bit here, and then it goes back up to infinity. Well, this here is the interval of convergence, and then half of that is the radius of convergence. Or the radius, yes. So the radius of convergence is for the positive case, and then there's also a negative case because we have the absolute value. And a little bit of subtlety here is that our series might converge at here or here at the endpoints, but it also might diverge. So we know it converges for this magnitude here, but it might not converge for the endpoints. It might diverge. So that's something you need to check for. That's for the interval of convergence. So the interval of convergence, we know it must take the form x minus a to x plus a, but it could also take the form where this is a square bracket, or where this is a square bracket, or where both of these are square brackets. Okay, let's do an example. Let's try an example today. So I would like us to find the radius and interval of convergence of the sum from n equals 0 to infinity of negative 3 to the n x to the n over the square root of n plus 1. Okay, now to do this, what we're going to do is we're going to first use the ratio test. That's what we've always done in order to find our power series convergence. So what we will do is we will plug into our formula. So we get the absolute value of negative 3 to the n plus 1 x to the n plus 1 over the square root of n plus 2 times the square root of n plus 1 over negative 3 to the n x to the n. Okay, so first of all, what we can do is we can cancel out some negatives, and we can also take the time to cancel out any outstanding polynomials that we might have. What we end up getting is negative 3 to the x, or negative 3x absolute value, square root n plus 1 over n plus 2. Okay, so what we can do is we can divide by n, and this lets us take limits more easily. So we get 3 times the square root of 1 plus 1 over n over 1 plus 2 over n times the absolute value of x. So whenever we take the limit of this, we're just going to get 3 times the absolute value of x, of course, because this goes to 1, because these go to 0, so we get 1 over 1, square root of 1 over 1 is 1. So we get 3 times the absolute value of x. Now for the ratio test to be satisfied for a converging series, we need to be less than 1. So we set 3 times the absolute value of x to be less than 1. We can divide by 3, we get the absolute value of x is less than 1/3. So now we have a radius of convergence, which is 1/3. That's great. Now we need to put this in context, and to do that we need to find the interval of convergence. Now to find the interval of convergence, what we need to do is we need to look at the series at the endpoints. So the endpoints are going to be at the radius of convergence. So it's either going to be at x minus, or it's either going to be at minus a third, or it's going to be at plus a third. So we're going to check to see if the series converges at minus a third, and then we'll check for plus a third. So let's check for minus a third. So if we have x equals minus a third, then we get the sum from n equals 0 to infinity of negative 3 to the n times negative 1/3 to the n over the square root of n plus 1. Okay, so what we get here is we get a series that diverges because we are taking negative 1/3 to the n and negative 3 to the n, which becomes positive, and then we also have a p series down here where p is a half, which is less than 1, so that means that we diverge. On the other hand, for this series, for when we have x equals 1/3, we can use the alternating series test to prove that the series converges. So what we've determined is the series diverges at negative a third, but converges at 1/3. So it diverges at negative 1/3, which means that 1/3 is not included. And then we have a radius of convergence here, which is 1/3, and then we have 0, and then we have another radius of convergence, but then it converges at 1/3. So that means that we include that into our interval of convergence. So that means the interval of convergence means x is an element of open bracket, negative a third, comma a third, close bracket. So that is the interval of convergence and the radius of convergence. So it's a fairly easy concept to understand, just to make sure that you check the endpoints and to know how the ratio test works. In the next video, we're going to talk about how we can actually apply power series and how we can use them to solve problems in calculus. Thanks for watching.